All right, here are solutions to written problem 5 from Math 243. The idea here, we are getting into hypothesis testing, so a really important topic for the rest of the class. And I guess we'll just read through it. So suppose that the number of slices of pizza that an American eats in a month is right skewed with a mean of 20 and a standard deviation of 10. So maybe we can start by giving symbols to these two numbers. This standard deviation, it refers to the entire population, the population standard deviation, so it's sigma. Sigma is 10. And then this average refers to the population as well, so you're probably thinking the symbol we should use is mu. But we're going to save the symbol mu to mean something else. So the symbol that you'll use for these is mu naught. Think mu naught is like the baseline value that we're going to compare things against. We're going to compare the average amount of pizza that college students eat with this baseline value of 20. At any rate, if you read through the second sentence, we get into all the sample information. You randomly select 36. Here's my sample size. So n is 36. And here's my sample average. So x bar is 24. And you don't have to write it, but maybe I'll make the point that mu is the average pizza consumption, maybe. For all college students. So the idea is we already have a population average for all people, not college students. And then we have a sample of college students. And this is the population average of college students. This will be a mu, and this will be a number that's never given to you in these problems. At any rate, we're supposed to test the claim with 90% level of certainty. So that tells us that alpha is 10%, or 0.1 if you want to write it as a decimal. And now we can go through and do all these steps. So step 1 says state the null and alternative hypotheses. Sure. What you need to know about that is that the way you say my null hypothesis is H naught with a colon. And the way you say my alternative hypothesis is H1 with a colon. And I guess maybe we could start with the alternative hypothesis. That's always the claim that you're making. And both the null and the alternative hypotheses are always going to compare mu, this idea here that we talked about, the average pizza consumption for all college students, with mu naught, this population average pizza consumption for all people, the number 20 in this case. Mu will never be given to you. It's just the symbol mu. Mu naught will always be given to you, so it'll be a number given to you in the problem. And you want to compare those two. And like I said, we'll start with the alternative hypothesis here. This is the claim that's being made. So the claim is that college students, here it is, test the claim that college students eat more pizza than the average American. So that means there's a greater than sign here. That more corresponds with this greater than. That tells me it's a right-tailed test, although I don't need you to write that. My null hypothesis, that one's a little bit easier. It's also comparing mu and mu naught, but I always just put an equal sign in there. What that means is the population average for college students is just the same as the population average in the country. This is the skeptical point of view. You're saying that college students eat more pizza than everyone else? Well, if I'm skeptical, I'm saying no, they eat the same amount. Mu equals mu naught. Here's my null and alternative hypotheses. Step 2, or B, I guess, in this one. Sketch and justify the shape of the sampling distribution, then state the center and spread. Did I say skate? No, state. Sorry, I can't read. State and justify. Okay, so the shape is approximately normal, or you can just write normal if you want. I don't really care. And you're supposed to say why, and you're like, wait, why is it normal? That's weird. You said up here that it's right skewed, right? This is the parent distribution that's right skewed up here. But what I'm drawing is the, let's see if I even said it in here, sampling distribution. And there's this thing called the central limit theorem that tells you that the shape of the sampling distribution is approximately normal, regardless of the shape of the parent distribution, as long as n is large enough. The criteria we use in this class is that n is greater than or equal to 30. So my shape is normal because n is greater than or equal to 30. Center. Mu naught gives the value of the center. Technically, mu is the center, and you assume that the null hypothesis is true. But the number you put in here is mu naught. You can just say mu naught. That's fine. Finally, spread. It's tempting to think it's sigma, but it's not. It's sigma divided by the square root of n. And that's because what I'm drawing is the sampling distribution. This is the spread of the parent distribution. I have to divide it by the square root of n to get the sampling distribution. So sigma was given to me in the problem to be 10, and n was 36. So it's 10 over the square root of 36, which you can calculate if you feel like it, but I don't need you to. I'm fine just leaving it like this. Then step C, I actually do this twice. Sketch the picture for the classical method, so maybe that'll be in blue, and then again for the p-value method. So let's start with the classical over here, and then in a minute we'll do the p-value. So either way, I want to draw something that's approximately normal. Sure. And put a 0 in the middle to represent this center of 20. These are z-scores, normalized values. And then if I'm using the classical method, what I want to do is first depict alpha. So alpha is 10%. You're like, where's it go? It goes over on the right because it's a right-tailed test. So I'll shade in 10% over here. Label it as 10%. And then in a minute, I'm going to use my calculator to get a test statistic. And I'll have to figure out if the test statistic is in that shaded area called the rejection region. And well, the way I'll be able to figure that out is if I could figure out where that rejection region starts. And the number at which your rejection region starts is called the critical value. And it's what you need to figure out. I'm going to be short on room. So that you know if your test statistic is in there or not. So the way you figure it out is using the inverse norm function on your calculator. For inverse norm, you got to tell it the area below the point. So 10% is above it, so the area below, the area to the left is 90%. So the inverse norm function is under the distribution menu, second then variables. And then the area to the left of the point I'm looking for is 0.9. And I leave these as 0 and 1 because I want normalized values down here. I want z-scores. Hit enter, it tells you 1.28, give or take. That's my critical value. Can you do that? Sure. And now I want to find my test statistic. So the way you find your test statistic is you hit the stat key and go under tests. And the type of test we're running here is a z-test. It's the only type you've learned so far. And we don't have the data itself. I don't have this first college student ate this many slices. This second college student ate this many. I just have statistics about the data. And it asks me for mu naught, which we labeled up here was 20. Asks me for sigma, which we labeled up here was 10. X bar we said was 24. N we said was 36. And the claim, my alternative hypothesis, is that mu is greater than mu naught. So I'll select this third one. What I typically do is I calculate when I'm doing the classical method and draw when I'm doing the p-value method. So all I need is my test statistic, which is 2.4 in this case. So if 1.28 is here, 2.4 is way out here. I could say z equals 2.4 and add it to my picture. And that's the picture you want for the classical method. For the p-value method, the picture looks a little different. I still want to draw something that's approximately normal because the shape, center, and spread that I listed up here are still relevant. I still want 20 in the middle, and I'll depict that with the 0 because I still want normalized values. The nice thing about the p-value method is I don't need to do this inverse norm function because I don't need to find the critical values. I can go straight to stat, and then tests, and then z-test, and put in all this information. It's the same because I haven't changed anything. And then either calculate or draw. I'm going to do draw this time, but you can do either one. What you'll see is it'll shade a tiny bit of area. It's hard to even see where it's shading. My test statistic is so far over to the right, it's equal to 2.4 in this case, that the area right of it is almost invisible here. A couple little pixels maybe shaded in over here. It's really small. It's less than 1%. So that's me trying to shade in that really small area. The area right of that is my p-value. And if I state it as a percentage, it's 0.82%. So less than 1%. So that's how much area is to the right of this 2.4 is the idea with the p-value picture. And then I can make my conclusions. On my conclusion in the classical method, I'd say something like, because the test statistic, which in this case was 2.4, I like to restate the test statistic. You don't have to. Falls in the rejection region. Maybe I'll write ... I'll pick up on that in a minute. For my p-value method, I'm going to say because the p-value, which was that really small number, 0.82%, is less than alpha, because alpha was 10%. And then I'll say, I'll finish the whole conclusion. There is sufficient evidence to reject the null hypothesis. So anytime your p-value is less than alpha, it means your test statistic's in the rejection region. And it means you're going to reject the null hypothesis. Anytime you reject the null hypothesis, you say that the claim is true. So there is, so I can, maybe I'll say, conclude that college students eat more pizza. Sure. So if I can squeeze this in here. Sure, good enough. And just in case this is hard to follow, what I'm doing in blue here is I'm saying because the test statistic falls in the rejection region, then what I would do is kind of pick up right here. There is sufficient evidence to reject the null, so I can conclude that college students eat more pizza. So those are steps C and D, I guess. This was step D down here. Unfortunately, there's a step E, which says now suppose the claim was changed to college students eat a different amount of pizza. So the important information here is that this gets changed to different instead of more than. Redraw the two pictures from step 3. No need to redo any of the other steps. Okay, that's good. Maybe I can squeeze them in. So here's step E. Here's my classical picture. And here's my p-value picture. Maybe I can get them both to fit if I make them really small. Put 0 in the middle of both pictures. Maybe I should label. Here's p-value. Well, I'll label in a minute. Yeah, I'll put p-value over here and classical up here. Okay, well, if my claim is that mu does not equal mu naught, if it's a two-tailed test, which is what I get out of this word different, then what that means is my rejection region should be on both the left side and the right side. So that 10% from earlier shows up somewhat over here and somewhat over here. It gets split into the two different tails. Instead of having all 10 on the right, there's 5 on the right and 5 on the left. And so now I need to figure out, is my test statistic in either of those two regions? Well, I could figure them out if I knew my critical values. For my critical value, for this one, I have to figure out the z-score that's so far to the left. The area left of it is only 5%. I think you'll get negative 1.645 if you do that. 0 is still in the middle. And then if you figure out the critical value over here, you'll get 1.645. Where did those come from? Well, if you hit second and then variables to get into that distribution menu, and then go down to inverse norm. And if you pick whichever one you want to do, if you want to find this one, you'd say the area left of this is 0.95. And then the center and the spread are 0 and 1. And you hit enter, and it spits out that 1.645. So there's my rejection region. Those are my critical values. Now I get my test statistic. Find that the same way I did before. I go to tests and z-test. Put in all this information, which is unchanged. My claim is now that mu does not equal mu naught, so if you want, you can change that. Although what you'll see is that doesn't change your test statistic at all. It's still 2.4. So I don't know, maybe z equals 2.4. It's in the rejection region. Finally, my p-value picture, what I can do, I guess, I'll do it again, even though you don't even have to. You could hit the stat key and then go to test and then z-test. And put in all this information that's the same. And I typically, when I'm doing the p-value method, like to use the draw feature. The nice thing about the draw feature is it draws the picture for you. Although in this case, the p-value is so small it's hard to even see in the picture. But maybe you can tell they shaded in a tiny bit there and a tiny bit there. They shaded to the right of 2.4. That was my test statistic, so I'll depict that with the z. And to the left of negative 2.4, that wasn't the test statistic, so I won't put the z over here. And then this total shaded region is what's called my p-value, and in this case it's 1.64%. So this would be my classical picture, this would be my p-value picture. Note that I'd come to the same conclusions, essentially. I'd say my test statistic's still in the rejection region, I'd say my p-value is still less than alpha. So if I were making conclusions, which it doesn't ask me to do, but if it did, I'd still say, so there's sufficient evidence to reject the null hypothesis, so I can conclude that. And now instead of saying college students eat more pizza, I'd say college students eat a different amount of pizza. That's the idea with step E. And that's what you're doing in this problem.